Okay, we'll move on to the next topic. Observed wind damages in Leyte and Samar due to Yolanda. Will be presented by Dr. Ronaldo Emmanuel R. Aquino. Dr. Aquino graduated BS Civil Engineering and MS Civil Engineering, major in Structural Engineering from the University of the Philippines, Diliman, Quezon City, and he got his doctorate of engineering from the School of Architecture and Wind Engineering of Tokyo Polytechnic University in Japan. Dr. Aquino is currently a wind engineer at RWTI Canada, specializing in structural and cladding windows. Ladies and gentlemen, Dr. Aquino.
Good morning. As mentioned, I'm with RWTI right now. Just quick introduction, it's it's the first wind engineering consulting firm in the world. We went to Leyte and Samar in December last year as part of a joint JSCE, Japan Society of Civil Engineers, and PICE post-Yolanda survey team. And these are the survey team members, myself and William Mata and Justin Valdez, both from UP Diliman. So basically, we are essentially the wind damage survey team. With us was Engineer Ferdy Briones, who's making a presentation tomorrow. He was there, I think, the day after Yolanda, a day or two after Yolanda hit. So he knows the place very well. Engineer Noel Ortigas is also, I think, making a presentation tomorrow, basically from PICE, and they helped us with logistics, because again, they're familiar with the place. Dr. Eric Cruz, also from the UP Diliman, and the JSE survey team. Basically, their focus was on the storm surges. So I'm not going to talk about storm surges. Dr. Eric Cruz is going to present about storm surges and the results of their survey, I believe, supposedly today, but it has been moved to tomorrow. And Dr. Benito Pacheco, also from the UP Diliman, and of course, PICE ASEP, was the overall leader of the joint survey team. So as I said, we went there last December, more than a month already after Yolanda. So I'd like you to keep that in mind, because basically there were, of course, after a month, a lot of cleaning has been done already and things like that. We didn't see the exact damage condition due to Yolanda. So on December 12, we arrived in Leyte, in Tacloban. Actually, midday or mid-afternoon, and we just did a quick drive around Tacloban just to do a quick survey. And the very first thing we saw was there was just too much damage, overwhelming damage. We were just overwhelmed, and so on the second day, we decided to focus on this area just south of Tacloban. I'm sure you've probably heard of the place called Palo in Leyte. Basically, that place is mostly wind damage. That's why we focus there. While the storm surge team actually went to eastern Samar, like B1 and those places. So we separated we divided our group into two. So the wind team focused on Palo, Leyte. And then day 3, we visited parts of Samar, mostly southern Samar, eastern and western Samar. Then day 4, we went around Leyte, mostly from Tacloban and then down south, close to Dulag, which was close to the eye of the typhoon. And then day 5, we just went around Tacloban again, and we went to Manila. So this is a little map. So Leyte, this is Samar, western Samar, eastern Samar actually. So southern tip of Samar. This Tacloban Airport is somewhere here. Downtown Tacloban, I believe, somewhere here. This is Palo. This is, I think, Tanawan, Tolosa, and Dulag somewhere here. So approximate path of Typhoon Yolanda is somewhere, well, basically crossed Dulag. Although, of course, as you can imagine, we have typhoon winds, of course, or hurricane or typhoon winds are in a counterclockwise motion. So depending on where the path of where the typhoon is, the different parts, different places experience different wind speeds and wind directions. This is I took this off from New York Times website. Some of you might have seen it. So it showed again the approximate path of the typhoon, as well as I believe storm surge heights, inundation heights. But one thing that stood out for me here is this. I don't know if you can see it, but basically they're saying close to the eye of the typhoon, they're saying 75 miles per hour wind. So 75 miles per hour is approximately 190 kilometers per hour. It seems very low. I mean, the question is, where did they get that, or what's their basis for that? I found out actually that PACASA was able to measure a wind speed of around 190 kilometers per hour in Tacloban, but that was around 4 a.m. on November 8th. So that was not at the height of the maximum typhoon wind speed. Meanwhile, the Joint Typhoon Warning Center of the U.S. Air Force and Navy, I think, said approximately these are already converted into gust wind speed at 10 meters height. It's approximately 315 kilometers per hour. The Yolanda's actual maximum wind speed. The JMA, or Japan Meteorological Agency, which is the official meteorological agency by the WMO, World Meteorological Organization. They're saying, based on their measurements, that the maximum, again, this is converted, the maximum gust wind speed of Yolanda is 270. So again, I'd like to note these values are from analysis of satellite imagery only. So based on satellite imagery of the typhoon, they can estimate the wind speed close to the surface, close to the ground. And again, I converted them to gust wind speeds. So as you can see here, there are different, estimates of the wind speed, not direct measurements. This was a direct measurement, 190 kilometers per hour, but it was not at the height of the typhoon. It was not the maximum. So the question is, what is Yolanda's maximum wind speed? Of course, as you know, if you're doing wind design, that's one of the very important parameters you need, right, to design your structure. For example, you need the wind speed to estimate your design wind forces. So we don't know the exact wind speed due to Yolanda. And just to give you a background, from the current climate models for Leyte and Samar, the design gust wind speed, or 50-year return period wind speed, is 200 kilometers per hour for Leyte, 250 kilometers per hour for Samar. So if you're familiar with the MCP, that's zone 2, zone 1 wind speed. And then actually, most people, I hope most of you know this, but that design wind speed in the code, in the NSCP right now, for example, is for allowable stress design. When we multiply it by certain factors for LRFT or strength design, basically we can say that the structural damage is expected only if you design according to the current code for gust speeds higher than 250 kilometers per hour in Leyte, 315 kilometers per hour in Samar. So, in short, if the wind speed, if you have a new structure designed to the new code, you have wind speed more than 200 or higher than 250 kilometers per hour, then you can expect some structural damage if these were true. So again, we don't know. Meanwhile, for Leyte, let's just say the wind speed due to Yolanda is 315 kilometers per hour. For Leyte, that 315 kilometers per hour is approximately a 4,000, at least 4,000 year return period wind speed, maybe 7,500 year return period wind speed. So it's a very rare, obviously a very rare extreme event. Just quickly, I've been using return period, but basically take the reciprocal of the return period, that's the annual probability. So if we say 50-year return period, that means 2% chance of happening per year. 4,000-year return period is a 0.02% chance of happening per year. So every year there's that probability of occurrence of those wind speeds. So to estimate the wind speeds, and this is one of our objectives, or at least we tried to estimate the wind speed, Yolanda's wind speed on the ground in Leyte and Samar. Usually what we do is we look for clues. So we look for simple damaged structures which we can estimate the structural capacity, and then we can back calculate the wind speed. So for example, we found this light post in Samar. And then, steel, we were able to measure the diameter and things like that, the height, and so on. We can estimate the capacity. Again, it's just an estimate of the capacity. Then we can back calculate to estimate the wind speed. And the problem we had here is, we estimated, let's say, 315 kilometers per hour maybe is the minimum. So we tried different parameters as well for to define the terrain, to define your drag force coefficient. The only conclusion we can make is it looks like the wind speed, Yolanda's wind speed, at this location in Samar was at least 350 kilometers per hour. Again, that's just preliminary calculation. There's a lot of uncertainty. For example, so previously there was a house here, and it's not there anymore. We don't know if which went down first, the house or the light post, or we don't know if it's really the wind that caused the light post to fall down, to buckle, or is it maybe a flying object that was blown by the wind? So we don't know. So there's a lot of uncertainty, but. But just to give you an idea, that's one way of estimating wind speed due to a typhoon, if there were no measurements. They do this actually in Japan to estimate wind speeds from due to tornadoes. So again, this is preliminary. Just to let you know, a group from Japan, they were able to find this. So again, you have rebars, a certain size, and a certain deformation at a certain location. I think this is south of Tacloban. They can also estimate, excuse me, they actually took a sample of the rebar to have it tested. They can estimate capacity and estimate wind speed due to Yolanda. Unfortunately, the results are not yet in, so hopefully we'll get updates about that. Because again, it's very important to know what is the actual wind speed of Yolanda. No one really knows. No one has an exact measurement. Now, in terms of damages that we saw, obviously there were a lot of damages to residential buildings, because obviously there are a lot more residential buildings in the area. We went to, so as I mentioned, we went to Palo. Okay, it won't play. Anyway, we went to Palo and Leyte, and most of it is wind damage. You can see a lot of small buildings here, mostly residential. You can see a lot of tarpaulins. Most of the damage, of course, are on the roofs. See, here are two examples. You have a rather older structure here with timber roof frame, almost completely damaged roof. You have a slightly newer structure. Of course, it's a different geometry, but it's using steel roof frame and so on. Generally, this is what we've observed. Whenever you have wooden trusses, wooden roof structures, they're more likely to have more damage than newer construction like using steel roof trusses. And in general, when there's timber construction, anyway, more timber construction suffered more damage. So for example, here, I don't know if you can see from the picture, but this used to be a two-story building. you have concrete walls on the first floor and previously timber walls and roofing and framing on the second floor, so totally damaged second floor. And of course, you can just imagine all the damages inside the house as well as on the first floor, because of course this also had a timber floor. So in general, timber construction suffered the worst due to Yolanda. This is another example. You have concrete wall frames on the first floor, no problem. On the upper floor, you have timber walls and framing, as well as for the roof, you have complete total damage. And of course, there's a lot of falling and flying debris, like in this case, which could, for example, here you have a tree that fell down. It just so happened that the nearby building was not that near, so that house was spared. But you know, these things could happen during typhoon, even during Typhoon Millennium, for example. A lot of trees fell down and damaged adjacent structures. But at the same time, we don't know if you can see this roof sheet here. Maybe it was blown off from another building. It flew towards the tree, fell down the tree. So you know, those things can happen: falling and flying debris. And then this is a house in again Palo, still in Palo. Actually, there used to be 3 structures here, we were told. I think this is just the bathroom of an old building or structure here that's not there anymore. And actually, the roof here has already been reconstructed. Basically, we were told that they just basically replaced their old roof. So it was blown away by the typhoon, and then they replaced it. So this is a month after. So that's the sort of reconstruction that some of these residents are doing. In some cases, they're using, again, timber construction for reconstruction, maybe just for temporary shelters. But as I said, as I showed earlier, timber construction has suffered the most damages. So anyway, we also looked at schools, of course. Here, just a photo. You have 2 buildings, almost exactly the same, but you have damage to the roof on this building, but almost practically no damage on this building, which just goes to show the complicated nature of wind. Wind is very complicated. Sometimes you'll wonder why this wasn't damaged while this one was. They're practically the same location. There's a lot of different possibilities. For example, the wind might be coming here, so this was being protected by this building and so on. We don't know. This is another example. You have 2 buildings close to each other, one with damaged roof, one with not much damage to its roof. And then here, maybe you can see it. Of course, for our buildings, because we are in a tropical climate, we use, especially for school buildings, we use very large windows. Unfortunately, we don't protect them during typhoons. It's not our practice yet. It's probably difficult to see here. But of course, there were also damages to the windows, where the problem is if you have damaged windows, and air can come in through those openings, and then they can introduce uplift force to your roof. So if you have just an enclosed building, if you have a roof, wind will usually pull up the roof. But if you have an opening, let's say due to a damaged window, aside from the suction force on top of the roof, you have an additional pushing force from under the roof. So that's one of the reasons why. That's probably one of the reasons why there's a lot of roof damages, especially if there's damages to the windows. And again, of course, we use very large windows for ventilation usually because we're in a tropical country. Most of the year it's kind of warm. These are another examples. You have practically wide open buildings, which can again causes severe uplift on roofs and therefore severe damage on roofs. Here, I think they used timber construction here. Again, there used to be a building here. It's not there anymore. these are still school buildings. This was what I was telling you about. You have falling and flying debris, and wind itself could damage your windows, or damage the eaves or underneath the roofs, and then they can lift up roofs and so on. The previous schools I showed you were in Samar. These are in Leyte. Actually, there was also both storm surge and wind effects here. Here you can see the deformation of the coconut leaves pointing to the right, which tells us about the direction of the wind. But and there you have again big windows, damaged roofs. But again, there's the combined effect of storm surge and wind here, so it's difficult to say. But in general, the storm surge here didn't reach the roof. So mostly the roofs, the damages to roofs were due to the wind. So here, more extensive damage again because of the storm surge, of course. This is in Palo Leyte and actually UP campus there. So you have again timber roof construction and total damage. Hospitals also suffered the same fate. Timber roof construction, more severe damage. And again, aside from obviously from roof damage, you have interior damages. Of course, because wind and rain will come inside, so you have damages to your property as well, which is one of the side effects of roof damages or wind damages. This is another example of actually so it's not exactly a hospital, but medical facility as well. You have concrete frames, but you have timber roof construction. You have again very severe damage to the roof. But the other thing we've noticed also is the types of connections, especially of roof to frame. So I have a few more examples here later on. But here is an example of it's a government building. It's newer construction, mostly concrete construction, but it used very large windows, which were again damaged by the wind. Again, we don't know if it's because of the wind pressures itself or because of wind debris. In any case, it's very strong wind. And at the same time, you can see here there's a white spot. Actually, that's looking through the roof already, because the roof, although they used steel framing, the roof was also blown off. Again, I think because of the windows were not protected. You have again your roof wind pressures coming into the building and blowing underneath the roof. So yeah, and then this is the airport, the air traffic control tower. They already replaced the glass windows here, but all of those were damaged. This is one case where you have a relatively new construction. They have CHB walls on the side, but even the CHB walls were damaged. Maybe some interaction with the roof frame. Well, this is actually steel roof trusses already, but there was severe damage. You can see the walls, again, the walls disappeared. CHB walls, but here I noticed they use 4-inch CHB walls, which is not our usual practice of using 6-inch CHB walls for exterior walls. Another building, top floor damage, timber roof construction damage. I think this was a dormitory. A mall where you have again damages to your essentially curtain walls or glazing or windows. Another supermarket, a large span roof, and of course you have damages, a lot of damages indoors. This is an office space somewhere in Tacloban. And then a lot of trees also fell down. In this case, this is in Palo. They fell southward, which tells us, the wind blowing south, which means that the typhoon was still maybe offshore. Even those trees, those winds were already strong enough to make these trees fall down. And steel lattice towers. So this is one communication tower that fell down. Surprisingly, about 500 meters away, there's another antenna tower there. It's still standing. Of course, there are different types of structures. So, and they're at essentially different locations. We don't know what's the exact reason why this fell down, the other one didn't. Again, it's the very complicated nature of wind. Obviously, open steel roof structures. This is a basketball court. There used to be a roof, and then it got lifted up and then tossed to the side. So now it's there. This is the size of one man. You can see the size of the roof structure. And again, it seems there's some insufficient connection detailing. We think that's one of the issues. Essentially that led to the damages. Connection detailing especially between roof structures and supporting structures. So here you just have hooks, your rebars from the steel reinforced concrete pedestal hooked around the steel roof frame. But even concrete walls themselves were damaged. I don't know if you can see this, but here the wall tilted a little bit. Here you have again walls. Again concrete walls falling down. So, and this is a slightly newer structure. You have I think it's because of the interaction between the roof and the walls. But essentially, this tells us that maybe some parts of the structures might not be properly adequately designed for wind. So again, large concrete frames can also fall down, or also fell down. So just to summarize our observations, again we are reminded again that wind is a very complex phenomenon. In fact, if you look at our, let's say the NSCP, the structural code, it looks like the wind loading provisions are quite complex, but actually that's already simplified. Wind itself is much more complex than what we see in the code. Windows, glass curtain walls, it's not our practice to protect them yet. That might save roof damages, save us from roof damages in the future if we protect them. Mostly lightweight steel roof sheets and timber roof frames are the most severely damaged. And of course that leads to damages to interior contents of the sheltered floor. Again, inadequate structural connections, usually roof to frame or roof to support connections. Concrete walls, frames, and concrete frames might also not be designed for wind. I know this. Personally, I also designed just the roof for wind. Let's say if it's a small building. Previously. In old projects. So obviously very old buildings not yet upgraded. Very old tipper buildings, of course it's not required by law. Of course, yeah. And then there can be a lot of falling and flying, non-structural hazards, roof sheets, and a lot of other things can cause damages. And one of the things we observe, as I said, is some have already reconstructed essentially the same way as they have before the storm. So that might be a concern. But again, this is a very rare event. Again, just some ideas, unsolicited ideas maybe. Obviously, it's not our practice yet, but hopefully if we can convince people to at least protect their windows when a typhoon is coming, that might relieve some pressure off the roofs. If feasible, for new construction, concrete roof slabs might be better for wind, of course, and it has to be properly designed for earthquake. And if possible, avoid timber construction. I think in general we're doing that already, unless you can demonstrate that it will be sufficient. And essentially, roof sheets, screws and nails, connection detailing, even the concrete CHB wall systems and concrete frames. Basically everything that's exposed to wind, including curtain wall systems, I didn't mention here, but that falls under windows. They should be designed, they should be checked against wind. And this is just my opinion, but I believe there's no need yet to update the current wind resistant design standard, the NSCP 2010. So people have asked, after you landed, do we need to update the code my opinion is no. Basically, it has not really been tested yet. The damages we've seen are mostly due to either old construction or, essentially it's mostly due to old construction, not yet fully designed, not yet in full compliance with the latest standards. So I think education and implementation are key. In that regard, for example, ASEP, for example, we're doing some wind and earthquake engineering seminars around at different cities in the Philippines. So, of course, self-education and so on, of course, very important. So that's the end of my presentation. I hope we learned a few things. Thank you very much.
Dr. Aquino. We have one more presentation for this morning session. Then after that, we'll have open forum and then lunch. So, the next presentation is entitled Liquefaction Assessment, Disaster Risk Reduction and Community Resilience, Christchurch Earthquake. To be presented by